Today's exercises are on logistic regression. Let's begin by introducing the idea of logistic regression. Suppose that our feature space is the real number line, and we get a collection of observations, some of which are red and others of which are blue. What we'll want to do in this picture is separate the red from the blue classes vertically, just for illustration purposes. Suppose we want to estimate for a new observation whose class is not known, let's say here, the probability that that point is red. The probability, just subjectively, we might say, based on this picture, is quite small. Like we choose a value like this or something. And as we move to the right, we would still say, for example, here we think this is likely to be a blue point rather than a red point, but its probability of being red is larger, so we might estimate a value something like this. And at some point, we're kind of right in the middle, and we'll estimate a value of a half, and then for larger values, we would be more and more sure that the value we're looking at is red. So in general, the function which takes an input x and returns the estimated probability that that point is red might have a shape something like this, a sort of elongated S shape that starts at 0 as x approaches negative infinity and goes up to 1 as x approaches positive infinity. And if we try to think of the simplest function we can find that has this shape, one answer we might arrive at is the sigmoid function. Specifically the one defined by sigma of x equals 1 over 1 plus e to the minus x. So as x goes to negative infinity, we get a very large value in the denominator here, and we go towards 0. And as x goes to positive infinity, the denominator gets very close to 1 and we converge to 1. So this function by itself is not going to be good enough because it doesn't allow us to move left and right. If all the red points and all the blue points move left or move right, we'd like to be able to adjust the function accordingly. Likewise, if there's more or less separation between the red and blue points, we'd like to be able to achieve a steeper or less steep curve. So what we're going to do is give ourselves some handles, some parameters here in the exponent that allow us to make the curve steeper or move it left and right. And this is the way that we'll build inductive bias into the model. We'll assume that the regression function, in other words, the conditional probability that y is equal to 1, given that the feature capital X is equal to x, takes this particular form. Note that this is really a regression function, hence the name logistic regression, since the conditional probability that y is equal to 1 given x is the same thing as the conditional expectation of the indicator that y equals 1 given x. And since y is only equal to 1 or 0, this indicator is actually just equal to the random variable y. And the conditional expectation of y given x is the definition of the regression function. So note here that we aren't in any way estimating a blue density or a red density in this picture. We're directly estimating the conditional probability of being blue or being red. So this is fundamentally different from models like quadratic discriminant analysis or naive Bayes, which are built on the idea of estimating each density individually and then bringing them together only at the stage where we apply Bayes' rule to compute which class is most likely conditioned on the observed feature vector. Lastly, I want to note that it is possible to get exactly a logistic function as your regression function, because what we can do is make the class conditional densities Gaussians with the same variance but different means. When we use Bayes' rule to work out what the conditional probability is that the observation is red given a particular feature value x, it's given by this expression, and we can multiply the numerator and denominator by e to the x squared, and all of the quadratic terms cancel. So let's do the first problem. It's asking why is it not feasible to model the class 1 probability as a linear function of the feature value. And to see that, we just have to look back at this picture and think about what would happen if this gray S curve were actually a straight line. And what you can see is that at some point it will cross 1 and go above the band of values between 0 and 1, and it will also go below 0. So it's going to be returning nonsense values, except in the trivial case where it happens to be constant. So excluding this case where the class conditional densities overlap perfectly and we get a constant predictor, a linear function will always return some values in excess of 1 and some values that are less than 0. And those don't make sense as probability values. However, what we can do is take this range of values from 0 to 1 and blow it up into the whole number line by applying the function which takes a value p and maps it to log of p over 1 minus p. So this function is an increasing function from the open interval from 0 to 1 to the whole real number line. And if p is a probability, log of p over 1 minus p is called the log odds. So p over 1 minus p is called odds, and we're taking the log here. So this is called the log odds. And it's just a different way of looking at probability. And the point is that once you've blown this interval from 0 to 1 up to the whole number line, then it becomes meaningful to think about modeling this as a linear function of the feature values. In fact, that's another characterization of logistic regression. We're saying that the log odds of being in class 1 conditioned on the observed feature value is a linear function of that feature value. And the connection with the way we wrote it down earlier is that this function, which maps p to log of p over 1 minus p, is the inverse of the sigmoid function. So we can either say that r of x, the estimated probability, is equal to sigmoid of alpha plus beta x, or we can apply the inverse of the sigmoid to both sides, and we can say that the log odds is equal to a linear function of the feature value. So here's an example of a logistic regression model in a real-world situation. We're trying to predict a binary outcome, whether a student passes or doesn't pass a standardized test, given the following input values. And as we always do in the context of logistic regression, we're going to estimate something more fine-grained than that, namely the probability that the student passes, rather than just trying to predict whether they pass or not. So x1, x2, and x3 here, the values that we're going to collect are the number of hours that the student spends studying for this standardized test. x2 is whether or not the student has a tutor, so that's going to be 0 or 1. And then x3 is going to be the median household income of the neighborhood that the student lives in. And we're going to fit a logistic regression model that includes these three terms, and then also this cross term, which is x1 times x2. And we want to interpret the coefficients here. So beta 1 is the value that multiplies x1 in this model. So we can interpret it by saying that if x1 increases by 1, that induces an increase of 1 of the values being put into the sigmoid here. So if we move the sigmoid to the other side, we can say beta 1 specifies the improvement to the student's log odds of passing the exam per hour of studying. Likewise, for the other values, we can say they're giving the log odds boost we get per increase of 1 in the corresponding x value. And the most interesting one is beta 4, which gives the additional benefit of studying per hour if they have a tutor. So it's like the tutor accelerant. And it's worth really stressing, despite the way that these answers have been phrased here, that none of this is intended to be causal. This is true at the population level in the training data that the model is fit on. That if you know a student has a tutor, if beta 2 is positive, that's telling you their log odds of passing the exam is increased. But that's only true at the population level if you're talking about a randomly selected student from the training observations. If you talk about a particular student and you want to think about what things that student needs to do to pass the exam, that becomes a very different question. This is not meant to be a causally predictive model. The people whose data went into training this model were not making decisions based on the results of the model. And also the coefficients could be reflecting the influence of variables which have not been measured, which happen to be correlated with these variables. Certainly, for example, if your median income neighbor gets a raise at work, you wouldn't expect that to have any causal effect on your chances of passing the exam. On the other hand, at the statistical level, if it turns out that beta 3 is non-zero, the income of your median income neighbor does make a difference. But clearly in that case, that variable is acting as a proxy for other things that are actually influencing your performance on the exam. Okay, in problem 3, we're going to talk about actually fitting the model. So we have a parametric model here where a value of beta and a value of alpha are sought after. And we want to just find the ones that fit the data the best. And one simple way to say what it means to fit the data the best is just look at the likelihood. In other words, or the training data, work out what the probability density is, which, assuming the training data are independent, means just multiplying the probabilities output by the model across the training data. So what that's going to look like is that if we get a class 1 observation, we pick up a factor of r of that feature value, since r is the predicted class 1 probability. So let's say the first training observation was class 1, then we'll get a factor of r of x1. Let's say the second training observation happens to also be class 1, So we'll get a value of r of x2. Ideally, our model r is going to be large at both of those values, close to 1, so that our likelihood can be maximized. Let's say the third one happens to be class 0. We're going to pick up a factor of r1 minus r of x3, which again we'll hope to be close to 1. So we'd like for r to be small at the value of x3, and so on. And one compact way to write this is to say the product as I ranges from 1 to n, so that's over all the training observations. And what we can do is we can say r of xi to the yi. So if yi is 1, then we get r of xi, that's the desired factor. If yi is 0, then we're raising a value to the 0th power, and that's going to be 1, so it won't contribute to the product. And then likewise, we give ourselves a factor of 1 minus r of xi to the 1 minus yi. And that's the same idea. One of these two factors, either this one or this one, is going to be 1 and won't contribute to the product, and the other factor is going to be the part that we want, either r of xi or 1 minus r of xi, depending on whether it's a positive example or a negative example. So then what we can do is take the log of both sides and then negate. So taking the log turns the product into a sum, which will be a bit nicer to work with. And then negating turns the maximization problem, since we're looking for the maximum likelihood, to a minimization problem. And the reason we'd like to have a minimization problem is that we'd like to fit this into the same framework as our other machine learning models, where we have a loss function that we're trying to minimize. So again, product turns into sum, and then the exponents will come down. And then this negative sign, we're actually going to put into the exponent to avoid having to have a negative sign in this formula. And then this is the value that was advertised as the loss value we're trying to minimize. So that checks out. Using maximum likelihood estimation to fit a logistic regression model is the same as choosing the parameter values which minimize this expression. And note that although we didn't write alpha and beta on the right hand side here, it does depend on alpha and beta because r depends on alpha and beta. So you could write that dependency explicitly if you like. But the point is that you just want to choose the alpha and beta values that minimize this whole sum. So let's experiment with an example. Here we have some data that are linearly separable, and the problem asks us to show that there do not exist minimizing values for this data. So for example, we start here with a loss of 2.15, and we can decrease the loss. Already here it's down to 0.0521. What we did was make the graph steeper. So the steeper this graph gets, the closer the curve is going to pass to these red points and to these blue points, and all of that causes the loss to decrease. If there had been a single blue point over here, this green curve wouldn't have wanted to be up quite so high, because then it pays a very steep price for badly misclassifying this blue point. Since there is no blue point there and there's space in between to go from being very low to very high, we can just make this as steep as we want, and we can get the loss really small. Like here we've gotten the loss all the way down to 5 times 10 to the minus 14. So that's very small, and you can make it even smaller by just continuing to crank these numbers up, just preserving their relationship to one another in such a way that it crosses 1/2 somewhere in between this no man's land where there are no blue or red points. And so what we can say is that the optimization problem has no minimum. No matter what particular alpha and beta you choose, you can always choose another alpha and beta that are going to give an even smaller loss. So in problem 5, we want to think about what would be the problem with building a logistic regression classifier for the iris data set that we looked at last time. So we have, if we're just here thinking about sepal length and petal length, then our data look like this. And the first problem to grapple with is the fact that we have 3 different classes here. So we've been dealing with logistic regression as a binary classification problem, and it fundamentally is sort of a binary classification model. However, we can apply it in a situation where we have more than 2 classes by just forming one model per class, which is meant to distinguish that class from non-members of that class. So we'll build one model to distinguish blue from orange and green. We'll build another model to distinguish green from orange and blue, and a third model to distinguish orange from green and blue. And then each of those models is going to produce for each feature vector an estimated probability of being in that class as opposed to being in one of the other classes. And then we can just pick the largest one and return a final classifier that actually predicts one of these 3 classes. The first problem we run into is the one we just discussed. There's going to be a separating plane here. So the logistic regression could get as dense down here on the blue as we want and still have very small values up here. And maybe that's sort of okay if we just choose one particular really steep function But technically speaking, there is no minimizer to the minimization problem that logistic regression specifies. So there is no actual logistic regression function of best fit in this case. The class whose model is going to be most effective is this green one because it's not separable from the non-green ones. There's some orange ones kind of crossing this boundary here. Yet it makes sense that we'll be able to draw a line sort of through here and make the function increase up towards 1 as you move in this direction, where we have the green observations, and make it move down towards 0 pretty quickly as we move in this direction away from that line. When we think about the orange ones, though, we encounter another problem, which is that there are non-orange points above and below. And this is something that logistic regression is not going to be able to handle, because the logistic regression function necessarily has that elongated S shape. So there's some direction in which it increases most rapidly, and in that direction it will have the same S shape that we looked at in the one-dimensional case. By the way, we have a new trick here, which is this data frame macro that's shipped by StatsPlots. And it takes two arguments. One is a data frame, and the other is just a piece of code. And what it does is go through that piece of code and look for these symbol objects. So a symbol in Julia is very much like a string, it just has a colon in front instead of having quotation marks at the beginning and end. And this data frame macro is going to take this data frame, and whenever it sees a symbol here, it's going to check if that symbol is one of the names in that data frame. And if it is, it will insert that particular column of the data frame. So we can look at this data frame and see what it looks like. It has 3 columns: sepal length, petal length, and species. And so whenever we say sepal length, that's shorthand for the sepal length column of data frame. And that way you don't have to keep rewriting the name data frame every time you want to refer to some aspect of the data frame. And that's pretty helpful in this case because we have 3 different places where we're looking at one of the columns. We're grouping by species, and then these are the X and Y data being given to the scatter plot. So I have a picture here to illustrate this S-curve of the logistic regression function. And I don't want to walk through all of this code because we're going to do something very similar in the next problem. I really just put it up so that we can see the plot and see exactly what's happening. So this logistic regression function is really not able to say how to separate the red points from the green and the blue ones. And what it ends up doing is putting its sort of agnostic line where it returns a value 1/2. It puts it right along this kind of main axis that these data points lie along. So that's its way of saying, I don't really know if this is going to be red or non-red for pretty much all the points in the whole data set. It really avoids this place where it curls up close to 1 and then goes down close to 0. It avoids putting that on the points because it's going to pay a price, a pretty steep price either way. If it puts this really flat shelf down on the blue ones, then that's great. Then it's going to have this high part up here on the green ones, and it pays a big penalty for all those points. And the red ones in the middle are not really doing that great either. They should be classified as 1 with high probability, but in fact they're all getting values of around 1/2. So this logistic regression function kind of throws in the towel and just tries to avoid having to pay any particularly big penalties in this case. This stems from the fact that the actual density is more concentrated in the middle here, and you'd like to have a function which goes from low to high back to low again, and the logistic regression function just can't do that. It's necessarily choosing a direction and then increasing in this S shape along that direction. Okay, in problem 6 we're asked to think about what would we want to do to avoid these problems. So how can we imagine picking 3 sort of clumps of points in the plane in such a way that we don't have this problem that logistic regression really fails to capture what's going on. So one thing is we need to make the clumps overlap so we don't have this separability issue. But the other thing is we need to really avoid having one kind of right in the middle of the other two. And a simple way to do that is just center the clumps at the vertices of an equilateral triangle. And since Julia's logo is an equilateral triangle, let's just build something that looks like that. So we'll make clumps of 100 points each. So we'll choose red, purple, and green as our colors, since those are the colors of the Julia logo. And actually, just for fun, I want to use the exact colors of the Julia logo and not just generic red, purple, and green. So the way we can do that is by overriding this color names dictionary, which contains the RGB triples for each color name. Then we can choose as the means of our distribution the vertices of an equilateral triangle centered at the origin. So that's the top point, and then the lower left point should be the cosine of 210 degrees and the sine of 210 degrees in its x and y coordinates. And the point in the bottom right should be minus 30 degrees. And then what we want to do is just make a data frame that contains all of these points. So we'll start making a data frame that samples from this multivariate normal distribution. And then it needs to do that for each mu in the list of mean values. And then actually, for whatever reason, the distributions package gives you an array in wide form here where you'll just have 2 rows and many columns. And for a data frame, you want to think of it the other way, where your observations are your rows and your columns are your features. So we actually need to transpose the value returned here. And still what we have is a list of these matrices. We want to actually concatenate them together. So we make our list and then we splat it and vcat it, and that's going to vertically concatenate these. And then when we call data frame on it, it's just going to create a data frame that's populated with those values. We also want to include the color, so let's make another data frame. And we'll use a different data frame construction pattern, which is to put the name of the column and then use this arrow syntax, which is just making a pair. So this is going to be the first element of the pair, and then the second element of the pair is going to be the appropriate vector, which is just this colors vector repeated n times. But it's not repeated one after another. Rather, we want to repeat each entry. So we call that an inner repeat. And finally, we want to take these 2 data frames and horizontally concatenate them. We want this to be an additional column in the data frame that has these other columns already there. So this is what our data frame looks like. So let's scatter these data. Let's use a data frames macro again. So we'll use these first 2 columns as our x and y values. So that's x1 and x2 as symbols. We'll group by color again. And we'll also color by color. So otherwise it automatically selects the color. We're telling it here, no, actually the thing we're grouping by really is a color name. So you can just use that directly to choose the color. And then I have just a bunch of other plot attributes here that I want to incorporate. So this one is marker stroke width, which is making it so that there's no outline around the points. And then the rest of it's pretty self-explanatory. Aspect ratio of 1, we're turning the legend off. We're setting the Y limits, and we're choosing a frame style here. So it looks a bit like the Julia logo. The point is that we've done well because the data are reasonably nicely separated, but there's a little bit of overlap, enough to keep the logistic regression models from going haywire. So we're going to need to call this scatter function repeatedly, so let's give it a name. And then proceed with making our logistic regression model. So we want to define our R function, and here we do have to make the dependence on beta explicit because we're writing code and it has to actually execute. So 1 over 1 plus exponential minus beta transpose times. And then what we're going to do is, instead of keeping track of alpha separately, we'll just fold it into beta. So it's going to be one of the entries of beta, but then that means here we have to make 1 our first entry, so that that's going to hit this first component in beta and contribute our constant term. And then the values of x we'll put in here. So this is a vertical concatenation operator. 1 is the first entry, and then the entries of x are going to be the subsequent entries of this vector. So now we can define our loss function. And again, we're going to have to do it on a color by color basis. So conceptually here, what we expect is that there's going to be a line kind of coming through here separating purple from non-purple. Another one here separating red from non-red. Same idea, green separated from non-green. So first we include a term for each row in our data frame that does correspond to the given color. And then we include a term for the observations which don't correspond to that color. And then finally we fit our model to find beta hat. And what we're going to do is make this a dictionary so that we get different beta hats, 1 for each color. And it'll be keyed by color. And we'll start at a vector of all 1s. And let's see what that looks like. So we get some values. We'd really like to visualize this to see what's going on. So what we see is that our logistic regression does a very nice job of separating out the reds from the non-reds, So the gray region here is indicating non-red. So what you can see is that it's actually going quite steeply from this zone here, which is classified as non-red, to this zone here, which is classified as red. So this S shape is very flat here, and then rises quite steeply through this region into larger values up here. So you can see Z is 1. That's a value that's being heat mapped. And then very quickly, now it's already down to 5%. So it goes up from 95% to 5% just in this little range. Same idea with the purple. It's quite steep, coming from non-purple to purple, and green separating out as well. So we can put this all together into a single model that just predicts the best one. So we'll say predictive x is equal to the argmax of the predicted probabilities. And notice that we're not computing the overall proportions. We're just directly working with the probabilities here. And so this ends up working out pretty much perfectly. We have the blue and red and green separated in exactly the way you would do it by hand, knowing what these probability measures were. So in summary, the idea of logistic regression is to model the regression function, which computes the conditional expectation of y given x, as a sigmoid of alpha plus beta x, where the sigmoid function is this one, which maps the real number line into the interval from 0 to 1. Equivalently, we're modeling the log odds as a linear function of the features. Finally, to fit the model, what we want to do is incur a penalty of log of 1 over r of xi for each y equals 1 training point, and a penalty of log of 1 over 1 minus r of xi for each negative training point.